Hi guys, welcome to this page of the notes, and let's go ahead and keep going with doing these example problems where we're solving some real world situations here having to do with exponential and logarithmic functions, or we're using exponential and logarithmic functions to help model this natural phenomenon. Since I'm a chemistry guy, we're just going to keep rolling with these chemistry problems. I promise we'll get to some of the other sciences. I want to play some love to those other guys too, but I like chemistry, so these are the ones I enjoy doing. Here we go. Here's what I tell you. A paleontologist is examining the bones of a woolly mammoth, estimates that they contain, the bones, the remains that he found, contain 3% as much carbon-14 as they would have contained when the animal was alive. How long ago did the animal die? All right, well, here we go. Again, please notice that I did not give you this one. All right, this one's a little tricky, right? I've given you a percentage, right? But I've given you a formula in this one. And so you might be kind of like, torn, well, hold up a second. He gave me a percentage, but he's given me the continuous exponential decay formula instead of just the exponential decay where I have an R in it. What is going on? Now, you got to kind of be careful in these ones. This says, it's not saying that the rate of decay is 3%, right? This 3% has nothing to do with the rate of decay. Please notice the 3% is stating he estimates 3% of the original amount is what's left. This is not a decay rate. All right, so please be very, very careful when you're reading these problems. Don't just because you see a percentage assume that you need that exponential growth or exponential decay formula. It might be a percentage representing something to do with the initial and final amount, which in this case it does. So here we go. I don't actually give you an initial and a final amount, but I don't need to. You know that 3% of the original amount is left. So pick something easy, right? 100 is an easy number to take 3% of. What is 3% of 100? Yeah, it's 3. I bet you didn't even need a calculator to do that. So here we go. If I do an initial amount of 100, my final amount is 3 equals 100 E. Do you recognize this number? 0.00012. That was the value of K we got on the previous page of the notes for the half-life of carbon-14. Yeah, there it is. So we've got negative 0.00012. And I want to know how long ago did it die, so we're going to be solving for T. Well, guys, no surprise here, right? I divide by 100, right, and I get my percentage, 3%, but I get it as a decimal, 0.03. 3 divided by 100 is 0.03, right? Shouldn't come as any surprise that I wind up with that as my ratio. And it also shouldn't come as any surprise to you that my variable I'm trying to solve for is in the exponent position, right? That t is up here in the exponent. I need to get it out of the exponent position in order to solve for it. Since I have an exponential function with a base e, we're going to take the ln of both sides. In fact, actually, I'm going to skip that step. You guys know at this point, we've done it twice. Ln and e cancel each other out. You'd be left with just the exponent. Feel free to just jump straight to that. In order to solve this guy for t, that's multiplication, so I'll divide by negative 0.0012, and here's what we get. We get the ln of 0.03 divided by a negative 0.00012. If you do that, don't fat finger something on your calculator, I get 29,221 years. 29,221 years. That was so much fun. Let's do another. Here's what I got for you. A specimen that originally contained 42 milligrams of carbon-14 now only contains 8 milligrams. I want to know, how old is the fossil? Well, here we go. We got y equals a e to the negative kt. All right. Well, in this case, I give you the initial and the final amount. You started with 42. You now have 8. 8 is equal to 42. E. K, it's carbon 14, so it's that same number we used above, negative 0.00012. And I'm going to be solving for T. Go ahead and divide the 42 to the other side. 8 divided by 42 comes out to be 0.19. What this means, right, is that 19% of the original amount of carbon-14 is left, right? Up above, I did 3, if my original amount was 100, and 3% of it is left, 3 milligrams are left, right? And 3 divided by 100 got me the 0.03, just simply means 3% of the original amount. Well, this works the exact same way. I started with 42, 8 is left. What is the percentage? 19. 19% of the original amount of carbon-14 is still left in the remains. Actually, this is a fossil, so in this particular fossil. So anyway, here we go. I need to get that t out of the exponent position. It's a base e exponential function, so take the logarithm. ln, natural logarithm. And I got to get that t by itself, so we'll divide the negative 0.0012 to the other side. ln of 0.19 divided by a negative 0.00012. And if you do that on your calculator, don't fat finger something on your calculator, make sure you do the order of operations correctly. I get 13,839 Hey, I'm having so much fun, let's do another one. Here we go. A woolly mammoth specimen was thought to be about 12,000 years old. How much carbon-14 should still be left in the remains of that animal if it's 12,000 years old? This one's actually a little bit different. This time I've given you T, so let's plug this stuff in and see what happens. Well, in this case, right, I'm trying to figure out, right, what percentage of carbon-14 is left over. Well, the easiest way to find a percentage, right, is to find the percentage of 100. So once again, I'm going to make my initial amount 100. And the t is going to be 12,000. In this case, I tell you, after 12,000 years, what percentage of the original amount of carbon-14 is still left in the remains of this particular woolly mammoth? Well, this one actually, this is just a calculator problem, right? Please notice, I'm solving for y, but the y is already by itself, right? It's right here, it's all alone. So all you have to do is e raised to this power. I multiply these guys together first, then do e to that power, then multiply by 100. I think I did that for you here, and what I wind up with is, again, I would do negative 0.0012 times 12,000, then e to that power, then multiply by 100, and you wind up with 23.7. Again, remember, that's going to be a percentage, right? 23.7% of the original amount. The question asks, how much carbon-14 should be in the animal's remains? 23.7% of the original amount. And again, I know it's going to be a percentage because I just multiplied it by 100, right? And that's how you convert a decimal to a percent. You multiply by 100. So 23.7% of the original amount should be left after 12,000 years. All right, guys, time to pay some love to the other social sciences. So on the next page of the notes, we'll do a problem involving anthropology because we got to give some love to the social sciences. Head on over to the next page and I'll meet you guys there.